Okie dokie. Right, I'm tempted to try and turn off my camera, but I think if I do that, my laptop will crash, so I wouldn't bother today. Okay, guys. So today's lesson is GCSE Equilibrium Lesson 1, and Lesson 1 is Reversible Reactions, and you can see the learning objectives. So we've got 3 learning objectives today, but there are these extra tack-ons that I need you guys to recognize. So the first learning objective, I just need you to recognize the reversible symbol. I'm pretty sure everyone in the classroom can already do this, which is good. Yeah, the next one is understand that some reactions are reversible. You need to know that in reality, only about 20% of chemical reactions are reversible. It might even be less than that in reality. And we need to be able to kind of give reasons when those reversible reactions happen and why others aren't. The last one is know some important reversible reactions. Or the ones that I've then put on the classroom, which is state change, Haber process, contact process, direct hydration of ethene, the test for water, and esterification. All 6 of those come up on a regular basis on EdXL questions. So now I usually teach this. I usually teach these in a lesson called Industrial Chemistry. Industrial Chem. Apart from the test for water. The test for water is one that is not included, and state changes as well. But I tend to do those processes in industrial chemistry, and I've already got a YouTube video for that, and it's definitely worthwhile you watching it. Technically, now the stupid thing is, which drives me bonkers, is the fact that EdXL decided to remove industrial chemistry from its specification, yet it still asks the industrial questions. So it's really stupid. Metal extraction comes up a lot as well. The blast furnace, electrolysis. So they still ask it, yet they took it off the specification, and it does upset me a little bit. Okay, so I think let's tick off the first learning objective, and I'm pretty sure that most people already know this one anyway. So this symbol, yeah, that symbol there stands for reversible reaction, and I'm pretty sure that everybody already knows this. Yeah, reversible reaction. Now, at the end of this topic, I'm actually going to come back to that symbol because I really need to reinforce that this symbol, that this means reversible reaction. That's all it stands for. Because what tends to happen is students get to the end of this topic and they tend to think that it now stands for equilibrium. And it really doesn't. This symbol simply states that the reaction is reversible. Yeah, whereas this one is irreversible. Irreversible. It means that the reaction is sometimes described as unidirectional. I always like using that because I use that an awful lot in A-level. Unidirectional, goes in one direction. Yeah, one direction. Unidirectional. Yeah. So irreversible, the arrow is going in one direction, reversible, going in both. And then with this half head arrow, please nota bene, it is not that. Please don't do that. Yeah, lots of students tend to, and it is a mistake, so please try and avoid it. Okay, so since we recognize reversible as a symbol, now we need to describe what a reversible reaction is. So the question is, what is a reversible reaction? Now, a reversible reaction. So can I just point out that sometimes this is just simply given as the definition, but the thing is the definition is never actually asked. They never say give the definition of a reversible reaction. That has never been asked in my 15 years of teaching. But what they do say is, what is a reversible reaction? And it's kind of interesting that they do that. I don't know quite why. They seem to have a distinction between the two questions, and I don't really understand why when they are the same. But this is one that does get asked. So I'm going to put it into the class. So Ashley, what do you think a reversible reaction is?
I'm pretty sure you explained this before, but I forgot.
Okay, do you want to have a guess? Have a stab. That's me stabbing something, by the way.
I remember you said something about the products being able to like if it bonds together, you can like break the bond or something.
I like it. So yeah, so when a product can turn back into the reactants, very reasonable. So do you think there would be any conditions that need to be mentioned here? Because one of the things that, can I just point out, so I'm gonna say something now which I hate it when chemists say this. There are some chemistry teachers out there which will say to students in class, they will say, all reactions are actually reversible. And I absolutely hate that, because that is just not true. Yeah. So that statement, that I shouldn't say it's incorrect, but that statement which I don't like. So the statement is that all reactions could be considered reversible. Rue, why do you think a teacher might say that? Why can a chemistry teacher say this to students?
Because there's probably a way where you can force certain conditions to force the particles to rearrange themselves in the specific way you want.
I like it. I like it. That's perfect, Rue. It's the idea that we could force products to rearrange back into reactants. I like it. Thank you, Rue. And you said the key word there, which is conditions. Like we could put them under pressure. We could contain them in magnetic fields. We could do all kinds of clever stuff to try and reverse reactions. But what we realize that this whole thing is by using extreme conditions. And that is what makes this sentence so ridiculous. Because if I take a piece of paper and I burn it, yeah, if I take a piece of paper, a piece of parchment, Shanley's done an essay, and we decide to set fire to it. Yeah, we decide to set fire to it. And I'm going to ask Shan, what did we turn your paper into?
Ash? What do you mean by that?
I like it. So the ash, by the way, can you tell me what element the ash is?
I want to say carbon.
Yeah, well done. So we've reacted this with, I don't know why it's doing that. We reacted the paper with oxygen from the air, and we've turned it into carbon, which is a solid, and that's otherwise known as ash. Yeah, what else have we turned it into, Shan? Remember, it's combustion, Shan. Don't overthink this.
Water.
We're going to make water vapor. I love it. What else are we going to create? Probably. We're probably going to create a little bit of carbon monoxide. We're probably going to create a little bit of carbon dioxide as well. We're going to have all of these reactions going on. It's going to be a nightmare. And the concept that we could take all of this stuff and turn it back into Shanley's essay, what's the chances? Would everyone agree that this is completely and utterly ridiculous? Would everyone agree with that? Isabel, would you agree?
Yeah.
Because the idea of being able to take carbon ash, water vapor, carbon monoxide gas, and carbon dioxide gas, and squeeze them together and reorganize them back into paper is just crazy, isn't it? It's just not going to do it. So when teachers say these sentences, it does drive me crackers. I'm like, that is just a ridiculous statement. And it is a statement that a teacher is using to make students feel like they don't understand it. This is not a helpful statement. So hang on a minute. So what now, based on the fact that if we could consider all of them being reversible, that we could put them under ridiculous conditions and turn them back into whatever we like, we now need to come back to this question. So what is a legitimate, and that's a bit of it's an interesting thing. I'm going to put legitimate. How do you spell it? Legitimate, Matt? How do you spell that? Legitimate. A legitimate reversible reaction. What we realize is that it is a reaction that can be reversed under the same conditions, as the forward reaction. Does that make sense, guys? I'm gonna stop putting it to the classroom and ask people specifically. Ruby, does this make sense?
Yes.
Yeah. So let's do an example of this. I think the example is really, really useful. And let's pick one of these. So what we could do is we could do a state change. I think that's really good because state changes are such great reversible reactions. So I'm going to ask a really funny question now, and I'm going to ask it to. I'm going to move through the class. I don't know everyone's pictures. Shan, are you the dog? Who's the dog?
Yes.
Yeah,
The brown dog. Yes.
Shan, what is the boiling point of water? I'm going to take liquid water and I'm going to boil it. I'm going to turn it into gas.
Well,
What's the boiling point?
100 degrees.
Perfect. The boiling point is 100 degrees Celsius. Right. Shan, what is the temperature needed to turn steam or water vapor? Either one of these two. Guys, you can add this to your notes and add these little extras as well. Steam or water vapor. They ask that at Edexcel quite often. I don't quite know why. Give another name for steam. It's really weird. Shan, what is the temperature needed to turn steam back into water?
Isn't it just 100 degrees?
Is the right answer. So what we actually realize is that when you go through a state change, because these temperatures, the boiling point is the same as the condensing point. That's why we don't ever bother to talk about the condensing point. Has anyone ever heard that as a thing? It's like, oh, guys, does anyone know what the condensing point of, I don't know, carbon dioxide is? No one ever bothers. We only ever comment on two words, boiling point and freezing point. That's the only thing we ever talk about. But in reality, we could look at them from going in the other direction. What this means is, at a state change, at that point, liquid water is reversible. Some of it will turn back into, the water will turn into steam, and then some of the steam will turn back into the water. This will happen. This reaction, and the key thing is they are both occurring at 100 degrees Celsius. Yet they're happening at the same temperature, the same conditions. And that's really cool. That makes a lot more sense. Now we can look at something and say, now we recognize what a truly reversible reaction is. One that will take place, both forward and backwards reactions, at the same temperature. By the way, if you'd like also, the other condition is pressure. So it's actually happening at the same temperature, same temp, and pressure. It's always nice to talk about conditions. You guys will need to know the temperature and pressure, because that comes up later on in equilibrium, because those are the two things that we're going to be changing. That and concentration. Anyway, so, okay, let's do another example. I love the fact that we've ticked off a state change. Let's look at another one. Now, the test for water is an interesting one. Because can anyone here remind me of what the test for water is? What's the test? I'm going to ask this to the. I'm going to ask Harris. Harris, chemical tests. You did it in year 10. I know it was hard. Everyone found it really difficult because you've just got to learn it, and you guys didn't learn it. Harris, what's the test for water?
Copper sulfate.
Oh, give me another word that needs to go with it. Oh, you've done so well. Well done for remembering it.
Copper 2 sulfate.
Oh, you're so close, Harris. I'm so impressed. Ben, can you give him the word he's missing?
Anhydrous copper sulfate.
Oh, look at that. You absolutely bloody nailed it. That was amazing. Anhydrous. It's the anhydrous bit, Harris, that you needed. Anhydrous copper 2 sulfate. I like it. Ben, can you now give me the color change, please?
From white to blue.
Yeah, check him out. Dude, I'm impressed. From white anhydrous copper 2 sulfate, and it will become blue. Dark blue. It'll be like this kind of blue. It'll become blue. I love it. Well done, Ben. Really impressed. Well done, Harris. It was a great effort. Great effort. That was a total failure. Yeah, it'll turn blue. I like it in the presence of water. So let's write an equation for that process. I went from white, and you'll notice I'm trying to keep with some colors here to make this. So we've got CuSO4. That looks like calcium. CuSO4. And then we added 5 H2Os. And what I formed was CuSO4. Oh, need to change to blue. That's important. Change to blue. Gonna rub that bit out. There we go. And I've formed CuSO4 dot 5 H2Os. And that now, of course, is blue. Now, I've done it as reversible. Now, can I just point out that this isn't really strictly true? Because the forward reaction here, the forward reaction occurs at room temperature. That will occur at 25 degrees Celsius. Whereas the backward reaction is an evaporation process, so it needs to be slightly higher. However, at this point, some students at this stage always say, well, hang on a sec, then you can't really call it reversible. And I'm like, well, okay, if we looked at it, we actually really looked at this. Well, the bottom reaction can occur at 25 degrees Celsius as long as it was in a very, very, very dry place. Can anyone tell me what the water will do at 25 degrees Celsius if it's in a really dry place?
Evaporate.
Yes, well done. Great job. It's going to evaporate. So the backward reaction can occur at 25 degrees Celsius, but we just don't tend to really talk about it since, you know, it's one of those things where if you wanted to dry it out, you're probably just going to evaporate it. That practical, by the way, we use that practical here. It's nice for me to mention calculations at this point. Yeah, this practical has a particular practical used in calculations. I'm just gonna go. Yeah, the practical here is empirical formula. Practical. It's empirical formula and water of crystallization. Yeah, water of crys. Because the reason why we use this one is because it does work really well. And the question always that students have is there really 5? Yeah, and you can actually prove this. You know, if you actually take solid hydrated copper sulfate and you evaporate it and then run the maths on it, yeah, if you start off with 10 grams of it, we will actually produce the exact masses that will provide us with 5 moles of water for every 1 moles of copper sulfate. It's a great practical, and they ask it a lot. You guys will remember doing this when we did calculations. These water crystallization practicals are fairly common. But it's nice to talk about it as a reversible reaction because that's the context they use it in. They run it in a calculation and then they run it in equilibrium as well. They go, explain why this reaction's deemed reversible. And you're like, because you can warm it up and turn it back into its product, its reactants relatively easily. Yeah? Okay, so we've looked at a couple examples. And we can definitely apply our symbol now. We know that that symbol means reversible. No, some reactions are reversible. So, okay, so what we need to do is we need to know that some reactions are reversible and some reactions aren't. So let's have a look at some reactions that really aren't reversible, ones that we would say, no, these aren't. So let's just do some irreversible reactions. Okay, so irreversible reactions include, number one, top answer, combustions. Yeah, combustions are really the classic here for irreversible reactions. We're going to take something like, let's do the example. I'm moving through the classroom slowly. So I've just done Ben. I've got somebody there. I've got Toby. Toby, can you please name this guy for me? Name that guy.
Propane.
Well done. Outstanding. Good job. I so love the fact that you guys can name organics already. It's amazing. You've no idea how good it was for us to do that in year 10. It was absolutely bloody brilliant. It's amazing. Right, I'm now going to go for Rue. Rue, what am I going to react with it if I want to do combustion?
Oxygen.
Absolutely. What is the source of oxygen in this case?
The air.
Well done. It's nice to talk about the word resource. Yeah. So oxygen, the resource. By the way, they often say that. What is the resource for oxygen gas? Because we extract oxygen from the air, by the way. Resource is air. Right. Now I'm going to go to when. When I'm going to have incomplete combustion to form a toxic gas. What am I forming? You can pass if you like, when.
I forgot.
Okay. That's okay. Everyone forgets at times. No problem. Gonna go for tongue. Tongue. Incomplete combustion to form a toxic gas. What am I getting?
Carbon monoxide.
And?
And water.
Well done. We always make water. By the way, we're not making water, actually. Technically, we're going to make steam. But yes, well done. Thank you, Tong. The toxic gas, when is carbon monoxide? This one here, carbon monoxide, is toxic. You actually need to know why. And the reason being is it prevents your blood from carrying oxygen. Binds to blood, binds to hemoglobin. Hemoglobin, preventing oxygen being carried. So you die actually of asphyxiation. You actually run out of breath. And then, of course, water vapor. I like it. So we've got incomplete combustion. We can balance that now. So I'm going to ask Vic, can you balance it for me, please? Can you talk me through it aloud as well?
You put the 3 on this carbon on the right.
Okay.
Side, product side. And then now you have to get 8 hydrogens, so you put a 4 on the H.
I like it.
Side. And that means that you have, my brain is not working, 7 on the other side, which means 3.5, but you can't do that, so you double everything up.
Well done. You star. That was outstanding, that Vic. Well done. That was a solid walk through there. Really, really happy. Thank you. That was great. That's amazing. Great job. Cool. So it's nice for us to see, and by the way, what a great equation to see a half appearing on the O2 and then the trick of doubling it. That was excellent. Well done. Okay. So this reaction, all combustion reactions are deemed irreversible. There is no way that we're going to be able to take these gases, and there is a main reason why. Would someone like to suggest why this reaction is a ridiculous one to try and reverse? By the way, propane is also a gas, by the way, so is oxygen. The reason being is in order to get the gases to go back together in the correct order is just not possible. Also, during the reaction, because we're not doing this in a sealed container, and this is something I'm going to come to in a second, so gases will escape. Gases escape. Now, this is technically, like, I've seen this done in questions. yeah, where they've given you a liquid fuel. The example that they did was they took this guy. I'm going to now ask, we're doing really well today on our organic naming. I'm loving this. I'm going to go for Moses. Moses, can you name this guy, please?
Is it ethanol?
Well done, Moses, you star. Our Friday night molecule. Yeah, ethanol. We love ethanol. So we've taken ethanol. We're going to add oxygen to it. I'm then going to go to Kieran. I'm going to do incomplete combustion to cause global dimming.
It's going to form water and carbon.
I like it. Well done. And what is the name given to the carbon if they say to you, what causes the global dimming? What do you say?
You say carbon particulates.
Well done. Outstanding, young man. That was great. Carbon particulates. Love it. And this causes global dimming. Global dimming. Isn't it awesome how all of chemistry starts to come? By the time you get to the end of GCSE, guys, you're just going to realize how much all of this all ties together. So we're going to take ethanol as a liquid fuel. We're going to burn it to make solid carbon and make water as a gas. Let's balance it. I'm going to ask on to the next person. Isabel, can you talk me through the balancing, please?
There's 2 carbons on the left side, so you need to put a 2 in front of the carbon solid.
Outstanding. Next.
And there is 6 hydrogen, so you put a 3 in front of that water.
Doing brilliant.
And then there's 1, 2, 3. There's 3. Oh wait. I think that's it.
Well done. It's now already balanced for oxygen. Well done. Isabel, can I just point out, I gave that equation to my A-level class, and all but one got it wrong. Can you guess why? What did they forget? What did they not see?
I don't know. Yeah, I don't know.
It was really, really interesting for me that, because I gave that to my A-level class when we were doing calculations. And as I said, out of 8 students, 7 of them got it wrong. And I wonder if, Con, could you guess where they made their error?
The ethanol.
Well done. They forgot, they just didn't see the oxygen in the ethanol. They saw the O2 and just went, oh, I need 3 of them. They just did that. They just did 1.5 and then doubled it. It was really interesting. By the way, you don't have to double in A-level. I love that. You can use halves in A-level. Just leave them in. It's great. But it was just really fascinating for me to see them make. They all made the mistake bar 1. And I was like, what did you all do? And they were like, I just didn't see the O in the ethanol. It's really, really interesting. So this reaction was a great one because, guys, which part of the reaction, bearing in mind what we did over here, which one now is going to make it a problem to turn it back into ethanol? I'm going to ask Nick.
Yeah.
Nick, which part of this equation, if they said suggest why this reaction would be difficult to reverse, which bit in the equation is going to be the answer? You can pass if you like.
Can I pass?
Yeah. Anna, any ideas based on this bit here?
I'm not sure.
It's the gases escaping bit. This bit makes it tricky, and it's all because of these state symbols. So the reason why this is tricky to reverse is because the water is going to escape as a vapor. So, okay. So here's the next question. So if we wanted a reaction to be reversible, so to have a reversible reaction, be possible, Right, what do we have? I'm going to then go back to the top. Ruby, what are we going to have to prevent? Ruby, you there?
Yeah, so I'm just thinking. The gas escaping?
Well done. We're going to have to have a reversible reaction be possible, we must close, notice my capitalization, close the system. We must close the system. In reality, by the way, I could have actually, do you know what's better than that? I know if you've written it, I'm sorry. We must have this is better, a closed system. Right, I'm going to ask Ruby again. Ruby, what do you think, if you were to guess, what do you think a closed system would be in chemistry? Definition. What? Go on. What do you think a non-closed system would look like, Ruby?
A system that could be open to any other.
Yeah. So if I said to you, name a piece of equipment in the lab that you would consider to be an open system, what piece of equipment would you choose?
Beaker?
Yes, well done. An open system, Ruby, outstanding, is a beaker. Ruby, why is it considered to be open?
It's open to the air.
I like it. Because if we've got a reaction, stuff can escape. Not only stuff can escape, what else could also happen, Ruby?
I guess elements from the air could get into the reaction.
Yes, well done. Stuff could get in. Yeah. I'm just going to put in. Stuff can escape and stuff can get in. That is not a closed system. That is an open system. So what we need to do is the definition of a closed system, Ruby, do you want to guess?
A system that... Sorry, I'm trying to think how you'd word it.
You're doing fantastically, Ruby. A system where something and something...
reactants and products.
Yes, well done. You're such a star. A system where reactants and products can neither enter or exit. A closed system. And by the way, it's really easy to close a beaker. Put a lid on it. I'm going to go to, if I take my beaker and I seal it, that is now a closed system. Got to have that, touch it. There we go, closed system. Nothing, no reactants or products can enter or exit. That's all you actually need to say, by the way. No reactants or products can enter or exit. You're done. Closed system. Nothing in, nothing out. You need the reactants and products is 1 mark, by the way. Reactants and products cannot enter or exit, 2nd mark. Just to let you know, the 1st mark is the one that everyone tends to miss. Yeah, people just tend to say, nothing can enter or exit, and they lose the 1st one. Just nice to mention it. Rue, just jumping to you, Rue. Rue, can you suggest what one hazard potentially from a closed system?
If you make a gas from like a liquid or solid, it's going to take more space, and if it's closed, the pressure inside will increase, and it could lead to your test tube shattering.
I like it. Guys, this is one of the problems that we have with reversible reactions, is the fact that we have to close the system. And what that means is there are possibilities of these exploding. Yeah, if you're making gases at high pressure and high temperatures, then you need to create a container capable of containing it. And they're expensive. So it's kind of cool to mention that, the dangers of a closed system. I'm just going to mention that over here. Nota bene. Yeah. Danger of closed system is ... gas products will raise pressure, could explode. Explosions. I'm really tempted to show you oh, I can't play a YouTube video. Oh, I wonder if it's working now. I'm really tempted. Guys, when YouTube is working, type into YouTube explosion at Haber plant, because the Haber process is quite a famous one. They use very, very, very large sealed vessels at about 200 atmospheres. And there was a plant in the US where a fire broke out in the chamber room, and the fire was happening in and around the vessel. It was all around the vessel, and the vessel continued to heat up. Now, they build these vessels to cope with high pressures, but of course, eventually the vessel ruptured, and the explosion literally wipes the entire factory from the face of the earth. It like vaporizes everything. It's so insane to watch it, because these vessels are that dangerous. They're quite scary, really. But as I said, it's an amazing video. It happened in Texas, I think, Texas or Utah, somewhere like that. Okay, so going back to up here. So now we've realized in order to have a reversible reaction, we need to seal the system. We need to close our system. Next, go back over here. Important examples of reversibles. Okay, I'm now just going to go through some of my reversible reactions with you guys so you can make a note of them. And then our lesson is over for today. So the first one was, I think, state changes. We've already done it. The Haber. Right, guys, can you make a note of this, please? The Haber process. So now I will do these individually as well, but it's nice to lay the foundations. Oh, do you know what I'm going to do? I'm actually going to leave it there because I'm going to get shouted at if I overrun because it's first lesson. So, guys, I'm going to leave the lesson there today. I'll end the recording and say have a great day.
Wait, Mr. Duncan.
Yes?
What other irreversible reactions are there that we should know about?
I've listed all the ones needed in the these are all the ones that you need to know, Shan. Those ones. State changes, Haber, contact, diode, hydration, test water, esterification. You're done.
Okay.
That's all you need, and I'm going to go through those in a separate lesson. So I'm going to end the video, stop recording. Have a great day, guys.